Look up at the night sky for a moment. We grow up believing that time is a universal constant, an invisible, steady river flowing at exactly 1 second per second for every living person, planet, and star in the universe. We assume that yesterday is locked away forever, tomorrow hasn't happened yet, and today is moving at the exact same pace for everyone everywhere. But what if the world's leading space agencies, quantum physicists, and cosmologists have already confirmed that this view of reality is completely wrong? What if time travel isn't a science fiction fantasy, but an operational reality that NASA engineers have to account for every single day just to keep our modern digital world from collapsing? In the next 30 minutes, we are going to break down the mind-bending scientific proofs, physical experiments, and real-world satellite data that prove time travel is not only physically possible right now, it is an undeniable feature of our universe. To understand how time travel actually works in the real world, we first have to dismantle a foundational myth about the nature of time itself. For hundreds of years, classical physics, spearheaded by Sir Isaac Newton, treated time as an absolute background clock. Newton believed that if you placed a clock on Earth, a clock on Mars, and a clock at the edge of the galaxy, they would all tick at the exact same speed, regardless of what was happening around them. Then came Albert Einstein. In the early 20th century, Einstein published his theories of special and general relativity, completely shattering classical physics. Einstein proposed something radical. Space and time are not separate entities. They are woven together into a single, dynamic, four-dimensional fabric known as spacetime. And the most shocking consequence of this four-dimensional fabric is that time is entirely relative. The rate at which time passes for you depends directly on two factors: how fast you are moving through space and how strong of a gravitational field you are standing in. If you speed up through space, your personal clock slows down relative to someone standing still. If you move into a region of intense gravity, time bends and stretches, ticking significantly slower than it does in deep space. This isn't a theoretical math trick or a thought experiment. It is a physical phenomenon known as time dilation. And it means that time travel into the future is happening every millisecond of every day. Let's look at the absolute undeniable proof of this happening right above our heads. High up in Earth's upper atmosphere, roughly 60 kilometers above the surface, high-energy cosmic rays from deep space collide with atmospheric molecules. These high-speed collisions generate subatomic particles called muons. Now, when scientists create a muon in a laboratory at rest, they measure its lifespan using precise particle detectors. A resting muon is extremely unstable. It decays into other particles in just 2.2 microseconds. That's 2.2 millionths of a second. Even if a muon travels toward the Earth at 99.98% of the speed of light, simple classical math tells us it should decay after traveling only about 600 meters. It shouldn't even get close to reaching the ground. Yet, when scientists place particle detectors on the surface of the Earth, they detect vast quantities of these atmospheric muons hitting the ground every second. How is that physically possible? The answer is time dilation. Because those cosmic ray muons are traveling so close to the speed of light relative to Earth, time for the muons slows down dramatically. From our perspective on Earth, a lifespan that should be 2.2 microseconds stretches out to tens of microseconds. The muon doesn't feel like its time is slowed down. In its own reference frame, it lives its normal brief life. But to us on Earth, the particle travels into our future, surviving long enough to hit our surface detectors before decaying. Particle physics confirms it every second. Velocity physically alters the flow of time. Now, you might be thinking, that works for subatomic particles, but what about actual human beings? This brings us to real human astronauts, NASA space missions, and the real-world proof that human beings have already traveled forward in time. Consider the famous example of NASA astronaut Scott Kelly and his twin brother, Mark Kelly. In 2015, NASA launched the landmark twin study. Scott Kelly went to live aboard the International Space Station for nearly a full year, while his identical twin brother Mark, also an astronaut, remained on Earth as a baseline control. While aboard the International Space Station, Scott Kelly was orbiting Earth at a speed of roughly 17,500 miles per hour, about 28,000 kilometers per hour. Because Scott was moving at such extreme orbital speeds relative to Mark on the ground, special relativity dictates that Scott's time moved slightly slower than Mark's time. When Scott Kelly returned to Earth after 340 days in orbit, the mathematical calculations were confirmed. Scott had aged slightly less than his twin brother. He physically traveled roughly 5 milliseconds into Mark's future. While 5 milliseconds sounds tiny to a human mind, in terms of physics, the threshold was crossed. Scott Kelly didn't just experience an illusion of time travel. His biological clock, his cellular aging, and his physical reality moved into the future at a different rate than everyone standing on Earth. The record holder for the human who has traveled furthest into the future is Russian cosmonaut Gennady Padalka. Padalka spent a total of 878 days in space across his career, orbiting Earth at incredible velocities. When you calculate the time dilation over his nearly 2.5 years in orbit, Padalka physically traveled roughly 1/44th of a second into the future. He is literally younger today than he would have been had he never left the surface of the Earth. So if high speed pushes you into the future, what happens when we look at the second factor controlling time, gravity? To understand gravitational time dilation, we have to look at the technology you rely on every single day to navigate your city, the Global Positioning System, GPS. Most people don't realize that the GPS network on your smartphone is absolute, daily proof that time travel is real and must be corrected constantly. The GPS network relies on a constellation of over 30 satellites orbiting Earth at an altitude of roughly 20,200 kilometers. These satellites carry hyper-precise atomic clocks that measure time down to nanoseconds. To calculate your exact position on a map, your phone receives signals from multiple satellites and measures the microscopic delay in the signal speed to determine your distance down to a few feet. Here is where Einstein's relativity becomes an operational necessity for NASA and space engineers. Effect number 1, speed. The GPS satellites are traveling around Earth at about 14,000 kilometers per hour. Because of this high orbital speed, special relativity causes their clocks to run slower than clocks on the ground by about 7 microseconds per day. Effect number 2, gravity. The satellites are located high above Earth, where the gravitational field is significantly weaker than it is on the surface. Because weaker gravity speeds up the passage of time, general relativity causes their clocks to run faster by about 45 microseconds per day. When NASA and satellite engineers combine these two opposing relativistic effects, subtracting 7 microseconds from 45 microseconds, they find that clocks aboard GPS satellites run 38 microseconds per day, faster than identical clocks on the surface of the Earth. 38 microseconds might sound like a split-second blip, but at the speed of light, a timing error of 38 microseconds would cause your phone's GPS location to drift off by more than 10 kilometers, 6 miles, every single day. Within a single week, navigation systems worldwide would be completely useless. Cars would be guided into rivers, and airplanes couldn't land on runways. To solve this, NASA and space agencies must intentionally program the atomic clocks on satellites to tick slower before launching them into space. They literally adjust the hardware to counteract the fact that space satellites are ticking in a different temporal reality than the Earth below them. Every time you open Google Maps or Uber, you are using software specifically calibrated to account for physical time travel. Now, let's take this concept out of Earth's orbit and push it to the absolute extreme: black holes. If Earth's weak gravitational field is enough to warp time by microseconds, what happens when you stand near an object with the strongest gravitational field in the universe? A black hole is a region of space where matter has collapsed down into an infinitely dense singularity, creating a gravitational pull so immense that not even light can escape its event horizon. If an astronaut were to travel to a supermassive black hole, similar to the famous scene portrayed in the film Interstellar, gravitational time dilation reaches extreme proportions. Imagine an astronaut hovering in a spacecraft just outside the event horizon of a supermassive black hole, while a second astronaut remains far away in deep space, watching through a telescope. Because the gravity near the event horizon is warp level immense, time for the astronaut near the black hole slows down to a crawl relative to deep space. 1 hour spent hovering near the event horizon could equal 7 years, 10 years, or even 100 years passing for the observer far away. If the astronaut spends just a few hours near the black hole and then flies back to Earth, they would return to a human civilization that has aged by centuries. Their children, grandchildren, and great-grandchildren would have lived full lives and passed away, while the astronaut aged by only a few hours. This is not science fiction. The mathematics of general relativity are unequivocal. Intense gravitational wells are literally functional, one-way time machines into the future. At this point, a critical question arises. We know how to travel into the future by using velocity and gravity, but what about traveling back into the past? This is where physics faces its greatest challenge, and where theoretical physicists at NASA and research institutions around the world are pushing the absolute boundaries of science. According to Einstein's equations, traveling into the past requires bypassing the universal speed limit, the speed of light. In special relativity, as an object with mass accelerates closer and closer to the speed of light, its relativistic mass approaches infinity, requiring an infinite amount of energy to push it further. This is why no physical object can cross the speed of light barrier in standard space. However, theoretical physicists have discovered mathematical solutions within general relativity that allow for shortcuts through the fabric of space-time itself, bypassing the speed of light without ever locally exceeding it. The most famous of these theoretical shortcuts is the Einstein-Rosen bridge, more commonly known as a wormhole. In 1935, Albert Einstein and physicist Nathan Rosen realized that general relativity allows for tunnels connecting two distant points in space-time. Imagine a flat sheet of paper representing the universe. If you want to travel from one side of the paper to the other, you have to walk across the entire surface. But if you fold the paper in half and punch a hole through both sides, you can step instantly from one location to another. A wormhole doesn't just connect two distant locations in space. Because space and time are bound together as space-time, a wormhole can connect two different points in time. If you take one mouth of a wormhole and accelerate it to near light speed, causing time dilation to slow down time inside that mouth, while leaving the other mouth resting on Earth, a temporal offset is created between the two ends. Stepping into one end would instantly transport you back out the other end, decades or centuries earlier in time. While wormholes remain theoretical on paper, scientists face a major physical hurdle: keeping a wormhole open. Standard gravity wants to instantly snap a wormhole shut before anything can pass through. To keep a wormhole open, physics requires a substance with negative energy density, or negative mass, known as exotic matter. Exotic matter creates a repulsive gravitational force that acts as an anti-gravity pillar, propping open the throat of the wormhole. And here is where cutting-edge modern physics gets fascinating. Negative energy is no longer just a theoretical concept. In quantum mechanics, the Casimir effect proves that negative energy densities can physically exist in laboratory conditions. When two uncharged parallel metal plates are placed nanometers apart in a vacuum, quantum fluctuations between the plates are restricted, creating a net negative pressure between them. Quantum field theory confirms that the building blocks required for warping spacetime exist at the subatomic level. Another incredible mathematical model for real-world time travel was proposed in 1994 by Mexican theoretical physicist Miguel Alcubierre, the Alcubierre warp drive. Instead of trying to push a spacecraft through space faster than light, the Alcubierre drive warps space itself. The drive expands the fabric of space behind the spacecraft while contracting space in front of it. The spacecraft rests inside a localized warp bubble of flat spacetime. Because space itself can expand and contract faster than the speed of light without violating special relativity, the ship moves with the bubble at superluminal speeds. In 2021, researchers at advanced propulsion physics groups and independent labs began refining Alcubierre's equations, demonstrating that lower energy physical warp models might be achievable without requiring impossible amounts of exotic matter. And because a warp bubble manipulates spacetime geometry, accelerating a warp drive past certain thresholds creates closed time-like curves, the formal physics term for a path that loops back into its own past. So why hasn't someone from the future visited us yet? Why aren't time travelers walking among us today? Physicists offer three major theoretical explanations for this classic paradox, known as the time traveler paradox. Explanation number one, the wormhole boundary rule. Most mathematical models for wormhole-based time travel state that you cannot travel back to a time before the time machine or wormhole connection was originally created. If humanity builds its first functional temporal wormhole in the year 2050, future travelers can come back as far as 2050, but no further. Explanation number two, the Novikov self-consistency principle. Formulated by Russian physicist Igor Dmitrievich Novikov, this law states that the timeline is inherently self-consistent. If you travel back in time to change an event, your actions end up accidentally causing the exact event you were trying to prevent. The universe prevents grandfather-style paradoxes by ensuring that all historical actions are already part of the locked past record. Explanation number three, the many worlds interpretation. Derived from quantum mechanics, this theory suggests that whenever a time traveler goes into the past, they don't enter their own original history. Instead, their arrival branches off a brand new parallel universe. Any changes they make occur in a new timeline, leaving their original timeline completely untouched. When you look at the big picture, the reality becomes crystal clear. Time is not a rigid background track. It is a flexible, moldable physical dimension. We know that time travel into the future is a proven physical fact because atomic clocks on satellites run faster, cosmic ray muons live longer, and astronauts return to Earth younger than their twins on the ground. We know that warping time through velocity and gravity is an engineering reality that powers our GPS systems every day. And as our understanding of quantum mechanics, space-time geometry, and advanced energy models continues to evolve, the boundaries between science fiction and physical reality are collapsing. We are all time travelers, moving through space and time at our own relative pace. The universe doesn't operate on a single universal clock. It operates on an interconnected network of endless personal timelines. Does knowing that time travel is an operational reality change how you view your place in the cosmos? Let me know your thoughts in the comments below. Hit that subscribe button to keep breaking down the mysteries of our universe, and I will see you in the next dimension.